Hello everybody. After the lunch break, you was not expecting me from that side, I suppose. yeah. Let's welcome Philipp from LINBIT, who will tell us a little bit more about the LINSTOR and DRBD. So a round of applauses and virtual applauses from the virtual people.
Thank you, Yvette. Yes, so I want to tell the CloudStackers what they need to know about LINSTOR and DRBD. Here we go. Starting with introducing myself and also introducing the company I represent. So the company is called LINBIT. We do open source software, and our business model is that we sell support subscriptions around that software. And part of the support subscription is you get support and you get access to the pre-built packages. So you don't need to go to GitHub, download it and compile it yourself. So what happened to me personally is, you know, when I studied, I became a big fan of Linux and open source. And when I graduated from university, I was looking for some interesting project I could do, and that is DRBD. Now, DRBD got a little bit famous, I would say. It's known around the world. Quite often, people don't know LINBIT, the company who makes it. And so it happened to me that my thesis just keeps me busy 22 years after graduating from university. And I'm more or less still working on DRBD. So you could say I'm a little bit passionate about replicating storage. So now let's get into it. Why LINBIT SDS? When is it a fit? Okay, I hide that on the slide. So it's also a good fit for container technologies, but that's not our today's topic. So it's a good fit for CloudStack and a few other technologies I'm not going to mention. And what kinds of workloads? Well, we love databases. Because it is a good fit when you require good I/O latency from your software-defined storage. So we have many of our customers and users running all kinds of databases and also message queuing systems, which is in a way another kind of database. Also analytic databases, here the big difference is you have this intermediate write intense phase and read intense phases. While the regular online transaction database, you need to have low I/O latency all the time. And this is the first part of the presentation. So I'm like doing a high level flyover, and then we go into the details. So what makes it unique? Why does it deliver good performance? And that is because of DRBD, because we have the data path completely integrated in the kernel, and that allows us to reduce the number of context switches, right? And what I'm talking here about, a context switch. So that's an operation in the operating system when it switches to CPU from one task to the other, and it lasts around 4 microseconds. And we want to get rid of as much units of 4 microseconds as possible. You know, when our storage media was hard disk drives, and you have seek times in, you know, 10 milliseconds or 4 milliseconds or something like that, you don't care about 4 microseconds. But the world has changed, right? NVMe SSDs are really fast, and there are other storage technologies even better. And suddenly, 4 microseconds is a lot. Yeah. Then at I/O time, we don't want to care about, oh, to which node do I need to send this write request? So we do all these decisions before we do I/O. So when the volume is allocated. That has one implication of that is that we cannot create bigger virtual volumes than the physical backing storage in our nodes. But I think that's not a problem. It's not a real world problem, right? It's like, I don't know, 20 years ago, people were talking about single system image clustering. The idea was that you create a virtual operating system that spans multiple nodes. Where's that technology today? Nobody needs it. We're going the other way around. So we have a very strong physical server and running many virtual machines or many containers on it. So our hardware is mighty. We need to split it up into useful pieces. Okay. We build on existing components as far as possible. And this is two reasons. Reason one, we are lazy, of course. Reason two, this is all open source. So we want to leverage the existing open source components. We are not reinventing the wheel all the time. And it also helps you, because in your data center operation, your people might already be familiar with CFS or LVM, and they can reuse their knowledge of these technologies. And I think that's an important point. It's very well suited to be used in a hyperconverged way. So that means you have your physical machines where CloudStack runs your VMs, and you use the same machines for your storage needs. So that saves investment, right? No dedicated storage machines. What is it doing? Well, it manages the storage on a couple of nodes. You should start with 3. It allows you to manage multiple storage tiers. So let's say you have hard disks in some nodes or in all nodes. You have SSDs and fast SSDs and NVMe drives in your nodes. You might need to serve multiple tenancies. And it might be necessary that you express the physical layout of your data center, right? So you can label your nodes with let's say, rack numbers or room numbers. And then later on, refer to these labels in the allocation policies. Okay, it does replication to be resilient against node and storage device failures. And it selects how it uses your network if there are multiple possibilities. Now, the next few slides go about things you know. So it's a building block for this software-defined storage system. So it's LVM, you know it, right? So you can combine physical volumes or partitions into volume groups and create LVs out of that. LVM has thin pools. So here a regular LV becomes a thin pool, and out of that we can create thinly allocated logic volumes. Anyone not aware of the difference? Everyone knows it. And also one nice thing is snapshots in the thin LV implementation, they share the exception space. So it stays performant even if you take multiple snapshots of the same origin, which is an important thing, because quite often you want to do things like take a snapshot every, I don't know, 5 minutes, every 10 minutes. Then we ship the snapshot deltas somewhere else, and then we automatically remove the snapshots. But still, for this kind of functionality, we need that the LVM layer supports multiple snapshots in a reasonable way. Yes, then there is software rate on the Linux kernel in multiple versions. Then there is deduplication. There is VDO. So that's now, let's say, the component to turn to in the Red Hat world. But let's not forget also CFS, ZFS, has its own deduplication. There are countless implementations of caching in the storage world. So here, a few important ones: DM cache, part of the device mapper framework, so accessible through the LVM tools. Bcache has about the same purpose, slightly different. DM write cache. The purpose of this one is to combine persistent memory and NVMe drives. Because writing to NVMe drives is still slower than writing to persistent memory. So that's purpose-built for this. You can ask at this point in time, is it still relevant? Because the fab to produce the Optane drives, so the 3D cross-point technology, was sold and is disassembled, so no more Optane drives. Oh, yeah, there are iSCSI and LIO and NVMe over Fabrics targets and initiators. You know what it is. CFS. I think CFS and Linux really became relevant since Ubuntu is shipping it, and other Debian distributions. I would say it has about the same capabilities as LVM, and I know this might be a confrontatory statement. I know there are so many fans of CFS who thinks it's the best thing since sliced bread. It has its features, but it's maybe not as unique as some think. Thin provisioning. So I mainly look at it on the level of block devices. I don't care that much about the file system itself. Okay, I promised that I will talk about DRBD, so let's do that now. It's another important building block. So DRBD is a software component for the Linux kernel, and it is like a RAID 1, and it mirrors between a local block device, something you have in your machine, and then it goes over the network to a target into the block device of another machine. And in the case you need to do a failover, this whole RAID 1 with everything moves to the other node. So here is an illustration I drew a long time ago. Oh, you hardly can see the boxes. But it shows us two Linux instances. So the orange box, if you can spot it, that's the Linux kernel. And here we have the stack. So in user space, you have running your service, your database, maybe in a container, maybe native. Then that database writes to a file system. Then there is a thing in the kernel called buffer cache that is very closely tied to the file system. And below that, usually the data would be written out to the disk scheduler, disk drive, and the hardware. And this is where mapping device driver goes in at this level. And well, what DRBD does, it mirrors everything through the network driver to a other node. And you see also the arrows going the other direction. So when something is written from the file system, it goes down to the other node. And also the storage device sends us back when it's finished writing that. And that's an important message, because then we know in the upper layers, okay, now it's safe. And in synchronous replication, what do? We send it to both disks, and we wait for the acknowledgement to travel all the way back. And here, this DRBD waits for both acknowledgements to arrive, and then it signals I/O completion to the upper layers. So it is transaction safe, right? When the database gets the message, this block of data was written to the storage device, than it is in both storage devices. And there's a lot of interesting details to it, like there's a difference between sending it to the device and flushing the device, for example. But let's not deep dive into that. So another way of looking at it is, okay, there is DRBD. On one side, we have the application running, and that is the primary node from point of view of DRBD. The other one is the secondary. And for many, many years, making it primary was an explicit operation. So there was a command, DRBD ADM primary something. And after that, you can mount the file system. Now, since DRBD 9, this is different. So since DRBD 9, you have the device file. And in the moment you open it for read-write, so in the moment you mount the file system, it promotes to primary by itself. And if we now try to mount it here, the mount will fail because it allows only one primary in this DRBD cluster. We can allow dual primary, but more on that later. Usually you don't and you do not want. That's important. Okay, it can also replicate multiple block devices together. That's so-called consistency groups. When do we need consistency groups? We need it when we run a high-performance database. And it's huge. Since it's so huge, we need a cheap storage volume for the table data, and we need an extremely fast storage volume for the write-ahead logs. So we have two volumes with different characteristics. One is cheap, one is fast. But when we mirror them, we need to mirror them together. Because if we are faster in mirroring the faster volume, and we have a failover, your database will not be able to recover from this, right? Because then the table space and the write-ahead log would be out of sync. So DRBD is capable of replicating multiple volumes in a consistent way. We can do up to 60,000 volumes in a single consistency groups. Nobody needs that. You need two. But yeah. For a long time, it used to be a two-node technology. That's over. Since DRBD 9, it's a many-node technology. So you can replicate from one primary to multiple secondaries concurrently, and you can switch these replication links from synchronous to asynchronous operation at runtime. Since we do multiple volumes, we have the support for intentional diskless nodes. So this is a complicated word in the DRBD lingo. So when you're new to the subject, you can consider this is like an iSCSI initiator. With the only difference, in iSCSI you have one target. Here you have two peers with backing disks. So if you write something here, it is sent to both nodes concurrently. The acknowledgements are coming back, and then this MySQL daemon gets, okay, the write was executed. And you can be sure it's in two locations, right? Yeah, and those don't have a change tracking bitmap. And in the moment you go 3 nodes, you have a huge advantage to 2 nodes. In the moment you go to 3 nodes, you can enable so-called quorum algorithm. And quorum means only a majority of the nodes are able to promote something to primary, are able to change the data set. And this avoids a problem, it avoids the split brain problem. So if you search on the internet for DRBD and split brain, you will find tons of web page describing how they ran into the troubles. So my answer to that is always go 3 nodes. It doesn't mean that you have to have 3 replicas, right? So 2 replicas is enough, but a 3rd diskless also serves as the tiebreaker in a situation where not all 3 nodes are online. Okay, so over the many years, we are constantly maintaining and improving this. It got a number of bells and whistles. So maybe important to remember is whenever one node goes down, comes back up later on, DRBD has to do a resync, right? So it needs to copy over the blocks that were modified in the meantime. So DRBD will do that for you. So it figures out which of the 2 copies is the newer copy. It knows which blocks were modified on the newer copy, or maybe which blocks were modified on the other one before it crashed, and it needs to roll back these changes. So all of that DRBD takes care for you. Yeah, and it does quorum by now. Let's not talk about fencing, that's old stuff. Recent developments, well, we have all this PMEM stuff merged, fine grain locking, discard granularities. This is something I could spend hours on talking. So in the moment we got SSDs have an interesting thing. Their SSD contains bigger blocks. They're called erase blocks. And data is organized in erase blocks. And when you write something to the SSD, you write in small blocks, probably 4K or even only a single sector. And then there is a flash translation layer, FTL, and that maps it to physical blocks in the SSD. And it can write there, but if the SSD needs to make space available again, it needs to erase a bigger erase block. And from the operating system side, we can send down so-called discard commands to tell the SSD, okay, these blocks, we actually don't use them. You can make them free to have more room for maneuver for your FTL layer. And that's the so-called discard command. And the storage devices, the SSDs, can expose in what units they want to see these discards, right? And that's all very interesting. I could spend hours on that. And with the software layers, like LVM and ZFS, we get more complexity here. And for a replication technology like DRBD, it is very important to do these discards right. Because just imagine for a second, we have here a volume and here a volume, and this volume is completely empty. So it was completely discarded. But if we would very dumb simply read it here and write it there, we would write all zeros, but completely allocate it in the backend, or allocate it on the SSD, while here it doesn't need any storage. It's completely discarded. So DRBD also needs to deal with these not allocated areas in a reasonable way. Okay, I guess I'm losing in the details. Let's move on. Yeah, and what we're going to add soon is or let me explain. Currently, DRBD expects that the 2 nodes or the 3 nodes or whatever number of nodes it is, they are in the same network. There's no network address translation between them because it expects that it can connect in both directions. And this is something we have on the roadmap to also deal with situations where you have NAT between them. Okay. So far, I was talking about a lot of building blocks, right? About these building blocks to slice the storage into smaller pieces like LVM and CFS and taking snapshots. I was talking about DRBD, which does the replication part. And there are even more building blocks like looks for storage encryption. I mentioned all the caching layers. And now we have a whole toolbox to build interesting storage things in Linux. But it's like a disorganized toolbox. So most of these tools come with their own management tools. And now I'm coming to what is LINSTOR about. LINSTOR about is a cluster manager, a distributed application that talks to all these tools, but gives you one consistent API. And it also does the allocation of storage requests to different nodes. So this is the shortest I can express it. Yeah, so all you need is a number of Linux nodes, something that wants to consume storage, like CloudStack, and okay, let's go into an example. I think an example is the best way to explain it. So here we have a cluster of 6 nodes, and it's hyper-converged. So we're running the VMs on these nodes, and we have built-in storage devices. And when we get the request that we want to have a new virtual volume from the hypervisor orchestrator, we say, okay, where is that VM going to run? And we try to allocate one replica, one logic volume of exactly that size on this node. And then we select some other node for redundancy purpose. So, and for the black VM, we have it here and here. So what you see is we have one replica where the VM is running. They are co-located. And that means for read requests, it never goes over the network. It never goes through the network stack, right? So for reads, it's extremely fast. So I often get the question, how does this compare to Ceph? Just think for a second. In Ceph, this would go over the network and it goes through an object layer. No, here, the read block command comes in and goes to the disk drive. And the overhead, you cannot measure it. It's in, so for reads, this is the best what you can do. For writes, okay. For writes, we need to replicate them. So we add network latency. And yeah, and LINSTOR will always try to co-locate these things if possible. Now, let's say you need to migrate a VM because there were too many VMs running here. Okay, no problem. This request goes through CloudStack to the CloudStack storage driver, and LINSTOR changes the DRBD configuration, and it adds a diskless node to this DRBD config. So here the block device becomes available, DevDRBD, but now all reads and writes need to be shipped to the other nodes. But KVM can migrate the VM immediately to this node. And then you can decide if it stays like that for, let's say, 1 hour, or you define a time window, let's say, in the night between 0 and 4 a.m. Then you want to migrate the storage to the VM. So that would mean we allocate here a new logic volume, let DRBD resync all the data blocks in that, and when that is done, it removes the third replica because, let's say, the policy only wants 2 replicas. Okay, I hope this gives you a picture of how this works with diskless assignments and that they can move around. And when you hear about the limitation that DRBD can only do 32 nodes, that means the black VM can have its volume replicated to 32 nodes. What does it mean for the whole cluster? Nothing. The whole cluster can span hundreds or thousands of nodes. Only a single volume can only be on up to 32 nodes, which nobody wants. I think 2 replicas is good, 3, maybe 4, maybe 5. I need to add something to that. But you don't need 30 replicas of a volume. And the LINSTOR cluster is not constrained by that. So it can be hundreds of nodes. Okay, so that was LINSTOR by example. Now let's go to the LINSTOR architecture. So the most important building block is the LINSTOR controller. Number 2 are the LINSTOR satellites. So you have one controller running in an active LINSTOR cluster. You might have standby controllers ready with automatic failover. And like a node agent, on each machine taking part in that, you have the LINSTOR satellite running. So the LINSTOR satellite is configuration-less and stateless daemon. So you install the package, system control, enable, make sure that it runs, that's it. And it gets contacted by the controller. So the controller establishes connections to all its satellites, and the controller distributes the work to the satellites. What is the work? It just needs to tell them, okay, we need to create a new volume, we need to resize a volume, we need to take a snapshot, we remove something. So this is that. And the whole structure you see here, it is not part of the data path. So if an application is writing to a DRBD volume, it writes, and the DRBD replication runs somewhere across directly. It has nothing to do with this structure. So this is the control structure. It's so independent, you can even stop LINSTOR. All the existing volumes continue to do I/O. And what else do we have here? The LINSTOR controller exposes a REST API. We have a CLI and Apache CloudStack driver and a few other drivers, but they are not interesting today. Now, let me quickly explain the kind of objects you are dealing with LINSTOR. So the first thing is nodes. So you need to tell LINSTOR about all the nodes it needs to take care about. Resources, that is in DRBD lingo, like a container for a volume. So in most cases, you will have a single volume per resource. So sometimes I use these terms interchangeable. We have snapshots. I think that speaks for itself. We have storage pools. A storage pool is either a LVM volume group, a CFS pool, shared storage pools, and then resource groups. And you see here in the illustration, a resource group is somehow a central concept. I would say it's the most important. But what is a resource group? What is in it? And what is in it is just a name so that you can refer to it. And it has a description where to allocate storage. So it contains how many replicas do we want. It can also be one, right? It contains, should there be a caching? Should there be encryption? Should there be a VDO? It contains how do we allocate? So, for example, always in the same rack, but in different chassis. So all that goes into the resource group. And then the resource group then has a one-to-one mapping to a primary storage. What is it called in CloudStack? I don't know. I have it in a slide deck later on. So that's important to communicate with the workload orchestrator above. Okay, so then the storage layers, that's also part of the resource group definition. So most often it contains DRBD, but that's optional. Encryption, caching, NVMe, targets and initiators, some way to store data, and maybe deduplication. Okay. Yeah, I think I already mentioned it. The way or the granularity, how you can describe this data placement in the resource group. And similar to that, you can also express, if you have multiple paths on your network, you can express how it should do that. Yeah, now let's come to the connectors. So for CloudStack, there is a driver merge to CloudStack. It got merged with 4.16. And it got a little update that will be released with 4.18. It's already merged, so if you look at the nightly builds, it's already there. And there were, I think, two changes. One is that now the QoS, quality of service settings from CloudStack, are passed to LINSTOR. And LINSTOR uses then C groups to enforce that in the I/O stacks on the machines. And the other change is that now in the CloudStack build, the LINSTOR driver is compiled into its own jar file. And that's an important maintenance improvement for us as a vendor, because if we need to improve something in the future in the driver, we can ship just this small jar file instead of the whole CloudStack controller, right? Yeah, and right now it is made for QEMU, KVM hypervisors. I can share that we're also working with the Vates team, XCP&G. But it's not yet clear how the XCP&G driver and CloudStack, if and how all that fits together. I don't know. So as of today, I would say QEMU, KVM, that's supported. Yeah, here again, let me, I mentioned it in the beginning. LINBIT is a company. We need to pay our developers. So we have an offering. The offering is called LINBIT SDS. It contains LINSTOR and DRBD just prepackaged. Instead of you need to compile it from source. It is support. And it comes with a GUI. So we have, although I'm an open source guy and I hate it, we have we have a proprietary add-on, and that's the GUI. I can show you that then. But I would say the important parts, that's all open source. So the data path and the control path. Yeah, and here I have this slide that helps me to map all these different names. So in CloudStack, it's called a primary storage. That's it. And what's called storage class in Kubernetes, for example. So naming is hard. Okay, so here is the summary. So LINSTOR manages starting from physical, so it has commands to discover physical storage hardware, LVM or CFS on this layer, the block storage features, and then the replication and the access to the orchestrators. Okay, so that was the slide deck. I hope that you now helped me with a few interesting questions. And if you don't have questions, I need to show you the GUI.
Anybody with questions?
In the case that we need to consume storage from LINSTOR using an iSCSI protocol, is it possible to do it?
Yeah. Yes.
In order to connect VMware or other hypervisors to LINSTOR?
Yes, so there is an add-on project. It's called LINSTOR Gateway. And to explain it right, yes, so with LINSTOR Gateway, you select 2 or 3 nodes out of your existing storage nodes, and then you can create their highly available iSCSI targets or highly available NVMe over TCP targets or highly available NFS servers just from LINSTOR resource groups. And it's made with VMware in mind. So the NFS set is exactly what you need for VMware. The iSCSI is compatible with VMware. Only the NVMe over TCP is not, because the VMware requires a little bit more than the Linux NVMe over TCP target implementation provides.
Okay, is it a separate project? It's an open source project?
Yes, it's open source projects,
okay.
But part of what we support. So in case you become a LINBIT customer, you just type yum install LINSTOR Gateway, and here comes the packages.
Okay.
But everything of that is also on GitHub.
My second question is about storage efficiency. Is storage efficiency, I mean deduplication and compression, is it something that can be managed by LINSTOR, or it's outside of its scope?
Yeah. LINSTOR just leverages on the capabilities of CFS, for example, because CFS has deduplication, or in the Red Hat world on the capabilities of VDO. So just the existing ones. So you could argue or make the point that it is not as efficient if we would do that in a cluster-wide way, but well, it is what it is. So I would say, I mean, deduplication is mainly interesting if you run Windows guests, right? Yeah. So I think for that case, it's really reasonable.
So we have to choose either VDE, which is a Red Hat environment, or ZFS, which is Ubuntu or Debian environment.
Yes. Okay. I mean, yeah, that opens a whole discussion in itself. I mean, OpenCFS is available for RHEL and RHEL clones, but then there is no vendor support for it, right? And if you choose to go with vendor support, then I would say on the Red Hat side, you go with VDO, and on the Ubuntu side, you go with CFS.
Okay. And my third question is, if in a cluster we have many virtual disks working, is there a fragmentation functionality exist in the LINSTOR in order to make space while disks are deallocated and reallocated in case of we have...
Yeah, I think I get the question. So,
yeah.
So storage allocation to nodes, that's also a huge topic. So what LINSTOR does by default is it would spread out the allocations. So that means when you start with an empty cluster, and let's say you have 10 nodes, right? You create the first volume, you want to have two-way replication, it would choose the first two nodes. When you create the next volume, it would choose the next two nodes, and so on. And after 5 volumes, all of the nodes have a replica, right? Then it would look, okay, which was the smallest one? Where do I put the next? And so on. And then, yes, you can reach the point where all the nodes are pretty full, right? You request a new bigger volume, and it doesn't fit anywhere. And then you would need to reshuffle, you know, the small pieces from here to there, so that the bigger volume fits. It doesn't do this yet for you. Okay. So when the cluster becomes very full, you run into this fragmentation issue. Yeah.
My last question is about placement, data placement policies. Is it possible to change these policies after a while?
Yes.
Because you need to add a new data center, a new rack, in order to distribute the data more better, to have better failure resistance?
Yes. So the resource groups can be changed after they got created. So, but existing replicas will not start to move by themselves. I mean, I need to to explain that deeper. So let's say we have a cluster with a few nodes, and a node has some replicas, right? If the complete node fails, we lose the second replica of a few resources, right? LINSTOR doesn't do anything immediately. But after a certain time, let's say 1 hour or 24 hours or whatever you configured, it says, okay, seems like that node isn't coming back. So it starts to reallocate replicas for all those resources that should be two-way replicated. So it does this in case of a node failure. But it doesn't do it when you just add nodes. So it will not move the existing replicas to the new empty nodes automatically. I mean, if the need arises, it might be a feature we do in the future. Right now, our point of view on that is you who operates this cluster knows best what you want to move. And LINSTOR has the REST API and the CLI, and it's with reasonable effort, you can script it the way you want to distribute it.
Thank you, Philip. As we're quite running out of time, we have one more question. So if anybody else has questions to Philip, they have a booth next to the door, and you can continue the discussion there. So final question.
Okay. Hi, Philip. My last question to you. So the question is, how do you handle those if there's a replication happening on the target device, right? The target machine. The disk is faulty, or maybe it has got bad sectors. Does LINSTOR tackle or have some kind of a check to ensure that the faulty drives are not used while replication?
Yeah. So so dealing with faulty sectors, this is something we leave to the lower levels. So for example, if you would use CFS, that's something that's handled by CFS. So one way to describe LINSTOR is to say it is like what is Kubernetes for containers is LINSTOR for storage volumes.
Thank you very much. Round of applause for Philip.
Thank you.
So once again, if you have more questions to him, you can just visit the LINBIT booth, which is next to the door. Thanks.